Then, with great pleasure, let me introduce the Test of Time Award session. So, as I introduced also this morning in the welcome session, but let me just very briefly repeat this. It's the first time that at RSS, the Test of Time Award is being introduced. I pushed this forward because I thought it's, well, first, a really interesting award for a really impactful piece of work from about 10 years ago from an RSS paper. So this is the first point and purpose of this award, to just award great work. But the second purpose is also that I think that the Test of Time Award is a good opportunity to actually discuss how our field is developing and whether it is actually making progress and whether the development is actually in a manner where, you know, we get better and better in solving the problems, or is it not sometimes that we have a development where we switch the problems? So instead of solving the problems, we actually start solving new problems and think that all problems become irrelevant and discover new ones. And I think this discussion is really important for our field in general. And the Test of Time Award, I think, is a really nice opportunity exactly to get such a discussion going. Okay, so this was my motivation to push forward this new award for RSS. And today I'm very pleased to announce the first winners. So first winners of the award is a paper from the first RSS 2005, which is called GTSAM. And actually, it is not only rewarding a single paper from the RSS 2005, but also the journal version of that same paper. It's considered one piece of work, which was published together with Michael Kaess and Frank Dellaert, of course. Let me introduce Frank briefly. Frank is professor at Georgia Tech and also researcher with Google AI. He's done amazing work in SLAM and other things, optimization. The one thing that I know him most for is, I think when we first time really engaged a lot, is he was thinking about what is the big graphical model of robotics. Like trying to formalize all of robotics in one big graphical model. And I really liked this a lot. And this was also a time when I was working a lot on planning as inference, and I found this super interesting. And I quite still, you know, like the discussions that we had about this. What is actually the big graphical model of robotics? And I think it's a good question. And Michael Kaess, associate professor at CMU and was also earlier at CSAIL at MIT. He's really successful actually in SLAM methods and more also in computer vision, 3D reconstruction, doing also some application in ocean robotics. I've seen really interesting work. And I'm very, very much looking forward to the talk of yours, Frank and Michael. Please.
All right, well, let's dive right in. So let me first say that I'm very happy to receive the award and also very happy for the opportunity to speak about our work. So thank you very much. Let's dive right in. So 5 years ago, I actually did a sabbatical at a startup, and it was to help them build the most advanced flying AI on the planet. And that startup was Skydio. And this is a rendition of their first version of their consumer drone. And it's not immediately apparent from this product picture, but the secret weapon of this drone is that it has 12 navigation cameras all around the exterior. So, and these 12 navigation cameras give it 360-degree vision. Earlier this year, they actually released the Skydio 2, which is the second product. Again, much improved. Now there's only 6 cameras, but the 6 cameras are all hemispherical 4K cameras. So there's a large leap in 360 perception. And they also much improved the autonomy. So this is a very capable platform. And to introduce it, I will try to show a video. So I don't know how will this work over Zoom. It might be a little bit stuttery, and there is a little bit of a soundtrack. So forgive the marketing pitch here. So as you can see, the drone flies itself. It tracks a person. It creates a video of you doing your favorite activity, like mountain biking from the top of a mountain. It's not my favorite activity, but some people actually pay money to have this capability, and it's quite amazing how autonomous it is. You just, you know, You launch it and it will fly itself. All the video you saw in this clip there is no pilot, and that is one of the things that sets this product apart from any other drone on the market. To enable this, right, to deliver value to the consumer, we need to have an autonomy stack that has to support superior navigation, tracking, and motion planning, and do so at very low power. So in this case, we track features in all of the 12 cameras. We track the person that we're tracking that is now running around in this example. We build a representation of the world around us using sparse SLAM, and we estimate the trajectory of the drone. And the sparse SLAM solution, SLAM is a term from robotics, which means mapping and localizing at the same time, and allows us to build a very detailed 3D model of the world, and hence avoid obstacles in the environment. So at the core of all these problems, okay, is an estimation, motion planning, tracking, are optimization problems, where you optimize, you minimize a certain objective function. And typically, these objective functions are local in nature. So for a trajectory like this, the objective terms, the terms in the objective would only involve a couple of poses, right? And that locality, so Marc alluded to what is the graphical model underlying robotics. To Michael and me, the answer is very clear, and it is factor graphs. It captures the locality of these measurements exceedingly well. And we've experimented with other graphical models. So this is not something we came by in a flash. This took a couple of years before we really settled on factor graphs as truly a remarkable graphical model in which to work. So if a robot sees a landmark, for example, right, but the location of the robot and the location of the landmark can be modeled as variables, and the measurement is a factor that ties together the location of these two things in a local objective term. As the robot moves from time A to time B, there is some odometry measurement that also ties these successive motions together. And so you build a graph over time, and that graph is a factor graph because there is, its key distinguishing feature is that there is these factors that underlie the optimization. Factor graphs can represent many robotics problems, okay? So from tracking to optimal control to the sophisticated 3D mapping that we did at Skydio, here are 6 snippets of factor graph that illustrate that. So there is tracking, which is a really simple linear factor graph of the smoothness of a trajectory over time, and then measurements at different successive times. We can add discrete variables to that to maybe infer what the person is doing. You know, is she going straight? Is she turning? Is she, you know, doing a somersault? All these can be discrete variables about the behavior. We can plan the motion of a drone, of a robot, by phrasing this as a trajectory and optimization problem where we optimize for the controls and the state at the same time. That's typically well known in optimal control as collocation. And then we can do sort of the more typical things like mapping, SLAM, and structure from motion, which is an earlier problem from the computer vision community, which allows us to build 3D models of the environment. So factor graphs underlie all of these problems, or you can model all of these problems with factor graphs. They also expose opportunities for computational advances because of their deep connection with sparse linear algebra. And we'll go a little bit deeper on that, not too deep, but deep enough that you get a sense for it. And I won't go through these strategies to increase computational efficiency. I will say that one of the most successful strategies is a graphical model that we build on top of factor graphs, which is called the base tree, which was Michael's PhD work and has really found applications in many, many different fields and papers. And finally, and I want to stress this because I think this is one of the most important properties of factor graphs. that they are beneficial in designing and thinking about your problem, even aside from any performance considerations. And it's my hope that in this talk we will be able to show you how different things were made possible. I can only speak from my own experience over 10 years in both academic and industrial settings. Factor graphs have been the whiteboard medium to innovate on algorithms, representations, new factors. So it ties different groups within a company or in a research lab or a university even together with a common language. So that's a big introduction. I hope that you're now sort of motivated to listen to sort of the more in-depth talk. I will give a brief introduction of how we got from square root SAM to GTSAM, which is our open source library. Then Michael will talk about computational improvements. I will talk about pushing boundaries into different fields besides estimation. And then Michael will conclude in the last section with new computational frontiers. And in the outlook, I will try to wax philosophically about what this all means for the future and where we thought we would be by 2020. All right, so in smoothing and mapping, we are interested in inferring the trajectory of a robot and the map of the unknown environment, okay? So smoothing and mapping is contrasted with SLAM in that we want the entire trajectory. And if you build the factor graph of that problem, you can see that in a single instant, just visually looking at this graph, you can see the nature of the problem and the locality of this problem, right? You can see, for example, that some landmarks are very well determined because there are they have many, many measurements. You can see that there is this trajectory which forms the backbone of this optimization problem. And then you have these landmarks that maybe have 1 or 2 measurements on them. And you can think, without doing any computation, you can say, okay, that's going to be a very poorly inferred landmark. So from a representational point of view, this is great. And this is what we latched on to in 2005, 2006 as really a beneficial property of thinking in terms of graphs rather than in terms of matrices, which really don't have that intuition built in. But there is a one-to-one correspondence between matrices, sparse linear algebra, and these graphs. In fact, in the square root SAM papers, we show that the key computation in doing mapping and estimation is to take this large sparse matrix and factorize it into a square root. Okay, so the square root of this matrix is an upper triangular matrix, and hence the name square root smoothing and mapping. And what we also show, and what we really deepened over the years after that, is that QR factorization, which is the underlying mathematical technique, is really an operation on a factor graph which goes way beyond linear algebra. We also did some visual SLAM back in 2005, and we reported on that in the journal paper. Michael tamed one of these robots with a multi-camera rig. We used a mobile robot by the company iRobot, which is not a vacuum cleaner. That might be a foreign concept for many of you, but at one point iRobot created research robots. And the graphics from 2005 may look a little bit cheesy, but all the principles to do multi-camera visual mapping were there. So just wanted to sort of show this blast from the past to see where we came from and where we are now. The key points from these papers, from the square root SAM papers, they do stand the test of time. Okay, so the key points are threefold. Matrices and graphs are in one-to-one correspondence. Factorization of a matrix is really variable elimination, which is an elegant computation on a graph. And the key to performance is the order in which you do variable elimination. So variable ordering will come back in this talk as a key way to speed up computation. what we now know after working 15 years in this field is much more, right? And I already said these points, but I'll repeat them here for emphasis. Factor graphs is really the key graphical model that we work with now, and it represents many robotics problems. They expose opportunities to improve computational performance, and they're beneficial in designing and thinking about your problem, even aside from performance. So with that, I'll introduce the GTSAM. GTSAM is a open source library. It's written in C++. It has Python and MATLAB wrappers. It's BSD licensed, so it's free for you to use, and it really embodies all these ideas of doing computation on factor graphs. There are other libraries that do nonlinear optimization and optimization that you can use, but they don't speak the factor graph language natively. And I argued, and I will continue to argue, that having a library that implements directly what you have on the whiteboard, which are factor graphs, is really a boon for engineering and research. So I will now turn it over to Michael, who will talk about sort of the computational benefits of working with factor graphs and the relationship with sparse linear algebra.
All right, thank you, Frank. So I'll cover computational improvements in the context of navigation and mapping. And yeah, so if we apply this to a real sequence, right, and square root SAM here on the Victoria Park data set really shows how the sparsity is key to the performance. The Victoria Park data set, this was a truck driving through the park with a LiDAR sensor observing trees. And so the goal now is to map the location of the trees with the main goal really of localizing the vehicle, of recovering the trajectory of the vehicle. And as you can see on the right side, the corresponding square root information matrix of that estimation problem is indeed very sparse. And so this is a key to performance of these algorithms. All right, so while finding an optimal variable ordering to get that sparsity is NP complete, we can use heuristics, and we can also potentially use domain knowledge, and that really makes a huge difference. So if we just take the information matrix, so that's the square of the measurement Jacobian, and if we factor this, if we take the square root of that, we don't necessarily end up with a sparse matrix. In fact, most of the time not. So what we have to do is we have to permute rows and columns. This is well known in sparse linear algebra. And we use some heuristics, and depending on the heuristic, you get more or less sparse matrices out. And in particular, we can use domain knowledge to figure out how to break up graphs. So this, for example, a generalization of nested dissection. Kai Li here used nested dissection, which is essentially breaking up a problem into equal sized parts and then breaking these parts up again. So he broke up a 2D estimation problem into small parts that can locally be solved, and then in parallel even, and then these pieces hierarchically get combined together into at higher levels, and finally at the highest level we get the full map out. Now this is not an approximation, right? It's a computational concept to factorize this matrix, and the result is exact. We can also use, so I'm having some problem with advancing slides here. Oh, it skipped one. Okay, so Hyper SFM applies hierarchical nested dissection to the structure for motion problem. So he extended this to structure for motion. You see a reconstruction of Venice here, and you can split up the problem and again, make this computationally more efficient. And I'm not sure why this does not work. Okay, so breaking up graphs can lead also to other powerful paradigms, for example, for distributed mapping. So in this case, we don't have a central instance that can combine these pieces together, but the inference has to be distributed over a couple of drones. And there's also communication constraints. But again, the factor graphs allowed to find good solutions to this problem. One back. Somehow I have not full control over. Okay. So the base tree is a powerful graphical model that enables incremental smoothing and mapping. So the base tree really corresponds to the square root information matrix, the sparse matrix. That one can be understood as a directed junction tree. Junction trees are used in machine learning for inference. So they're quite common, but they're typically undirected graphs. In this case, we have a directed graph. So they are equivalent, but the tree version is much more useful. So in the sparse matrix version, it's difficult to do updates incrementally, while the tree can easily do that. And
do you want me to advance the slide for you,
sure,
Marc?
Please. Yes.
Yeah.
And so ISAM now, the incremental smoothing and mapping, edits the base tree when new measurements arrive. Right? We have already previously calculated a solution for all of these previous measurements that we have. We have a base tree. And now when new measurements come in as the robot moves forward, we can simply update the existing tree rather than starting from scratch. Right? And that saves a lot of computation, as you could see, because only the top, the red cliques on top are actually changing. So here's a synthetic sequence and animation of ISAM2. And you can see that the amortized cost here is actually very low, right? Most of the tree does not change in most of these steps. On the right side in this, you can see the Ed Olson's Manhattan Wall, the synthetic data set that is being created, and that corresponds to this graph. The graph is green. Green means low cost. There are a few points between where there are loop closures, where it would be yellow and maybe red even. This means that a lot of the cliques in the graph have been affected. Okay. And so ISAM has been applied in many applications, from mapping of aircraft carriers to experiments on the International Space Station. And this work is work by Ayang Kim with an underwater robot inspecting large ships. In this specific case, an aircraft carrier. And so the idea is we have onboard sensors, cameras, maybe sonar also. We use the measurements of the hull. If we revisit a location we've previously been to, we can align these measurements and then create a loop closing constraint in the graph. And so if we optimize this graph, we can keep the vehicle localized in real time. And that's necessary because there's no GPS available underwater. And one of the biggest success stories in GTSAM is inertial navigation. So pre-integrated IMU measurements really yield state-of-the-art visual inertial navigation systems. So the key here is that that inertial measurements are very different from others. They come at a high rate, 1,000 measurements per second. So we don't want to have to add variables at that rate. The graph would get too large. But we can reduce this to, for example, the distance between images by pre-integrating. So it's called pre-integrating because it's a bit tricky since you need to know gravity direction, but we're just estimating our orientation. If you do this right, you get very efficient and accurate solutions. And so in my lab, we have applied this to onboard navigation on a drone. So in this case, we have very low computational power, and we need to find something that strikes a balance between efficiency and accuracy. So the goal here is to do fixed leg smoothing. We keep a small number of variables, constant, roughly constant number. That means we have to marginalize out old information, which destroys the sparsity and therefore the efficiency. But we can do sparsification explicitly. And in the factor graph, right, we find a structure that keeps it sparse over time, and that provides efficiency. And so, yeah, this now, Frank will talk about pushing the boundaries here So talking about works that we didn't even think of originally when we started with localization and mapping.
Cool. So, so I will talk primarily. So, Michael talked a lot about the work that happened in his lab, in my lab at Georgia Tech, where we pushed these computational aspects. I now want to highlight, if I talk about navigation and mapping, it will be other people's work. And I also want to highlight some non-estimation mapping work that both we did, but also others have used factor graphs in sort of surprising ways. So I'll start with highlighting MIT's Chimera package. That comes out of the lab by Luca Carlone, and his student Antonio Rossinol is the first author on that paper. It was published at ICRA. And really, it uses factor graphs at almost every stage of the computation, and it blends stereo and RGB and semantics information into one annotated semantic map of the environment. And it's just spectacular work. And when I saw this, I was very, very impressed by how amazing it looks. And at this conference, RSS2020, Antonio will actually present something that is built on top of that, which is the dynamic scene graph work, where they build on Chimera and then adds the segmentation of objects and dynamically track people within this map. And so these graphs, this 3D visualization is really sort of what ideal perception looks like in my mind. It's a completely semantic decomposition of the space at many different levels. So it's great work, and I encourage you to go see the video by Antonio and then interact with him in the session. So one thing that we have not talked about, which by now should be an elephant in the room, is deep learning. So in 2012, our worldview changed in a way forever, because in both NLP and computer vision, earlier neural network literature, which sort of never really worked well, with the advent of GPUs and going deep in many layers, all of a sudden things really started working. And so this is a data-driven paradigm that now dominates research in many different fields and is increasingly dominating robotics as well. So it's really gratifying to see people like Jan Czarnowski, who works in Imperial in Andy Davison's lab. They took variational autoencoders, which is a deep learning technique, and trained it to represent depth images for reference images with a very low dimensional latent code. And the cool thing about that is that you can now cheaply evaluate whether a particular depth image agrees with reality and agrees with each other. And you can put all these things as factors in a factor graph and build a real-time dense SLAM system that uses deep factors as an inherent part of the system. So I think this is very exciting work where you blend factor graphs with deep factors. Factor graphs have also been used in estimating the state of much less conventional. So we've all been brought up more in the mobile robots world, and so it's really cool to see work from, say, Jesse Grizzle's lab at the University of Michigan. This is Ross Hartley's graduate work, where they took a biped, this is a Kaess robot, and do state estimation by taking factor graphs, and that reasons about visual information, but then coupling it with factors that know about the forward kinematics of a biped, or very importantly, how the feet interact with the environment through contact. And so I think this is very exciting. And this also has been picked up by another group. There is a group at Oxford, and this is work by David Wist and co-authors, where they used factor graphs for quadruped state estimation. So this is animal. This is a commercially available quadruped robot. And it's quite challenging to do state estimation, especially in terrain where there is mud and there is slip. And those things, I've dealt with that before in a DARPA project. If there is slip of the wheels, then sort of all bets are off. And so they've been able to integrate both the sort of the kinematics of this quadruped with visual information and visual inertial information and get really great results. So everything that we've talked about before now was really about estimation, okay? And when Byron Boots came to Georgia Tech, one of the themes that we worked on together with our students, Mustafa Makadam and Jing Dong, was can we use the same graphical framework to do motion planning? And Marc alluded to planning as inference. Factographs is all about inference. So can we do state-of-the-art motion planning with factographs? And the answer is a resounding yes, right? We created a factograph-based trajectory optimization algorithm called GPMP, where we use Gaussian process factors to encode the smoothness of these trajectories. We add a task-related objective as a factor. For example, in this case, the robot has to open a drawer. And we add factors for obstacle avoidance. So we build a 3D model of the world. And the obstacle avoidance factors sort of index into sign distance functions so that you can avoid obstacles. And of course, all the work that we did before for fast re-estimation in an incremental smoothing and mapping framework, so the work by Michael, can now be repurposed for fast incremental motion planning. And so that's our incremental GPMP algorithm. So we use that in my lab. This is work by a couple of master's students and Seth Hutchinson and me. The first author is Sen Wang, who tamed this fetch robot and later a Franca robot to plan artistic actions such as calligraphy. So input here is a Unicode of a particular Chinese character, and the output is an open plan to provide to the robot that draws this character. And my Chinese and Taiwanese colleagues assure me that this robot is now capable of writing at the level of an 8-year-old. So plenty of room for improvement, and we are working on that by integrating feedback control into this framework. So finally, a new student of mine, Mandy Chi, is working on incorporating robot dynamics. So it turns out when you plan motions for a robot at non-trivial speeds, you have to take care of the inertia of the limbs and the angular and linear inertia. And also, if you have an object, like you have a box that you need to put on a shelf, you really have to think about dynamics and how you can use the dynamics to your advantage to plan optimal motions. And so we took the dynamics formulation from the excellent Lynch and Park book, Modern Robotics, poured it into a factograph, and then gave it to the same incremental solvers that we use in SLAM, and came up with a very nice kinodynamic motion planning, which is published and available on arXiv. You can ask yourself, okay, there's planning, there's estimation. Can you do both at the same time? And the answer again is yes. So you can put trajectory optimization and motion planning in the same graph. And rather than explain this rather busy figure, I'll just show you a movie. This is again work by Mustafa and Jing. And here you see a mobile manipulator with omnidirectional wheels on carpet. And every roboticist will tell you, that's crazy. These things never do what you tell them to do. So what we do is we, over time, estimate the trajectory. And because we have a very fast replanner, because you use the base tree and incremental inference, we can now replan the motion of the robot at any time a new estimate from the trajectory estimator is available. And this is all done in a single graph, and we simply forward the pointer of time. So we get a smoothing over the entire action. Okay. So here I hope I convinced you that factor graphs are not restricted to simply estimation, although they've been very successful in that area. The last sort of big piece of this talk is going to be Michael, who's been really thinking about how we can support new computations with factor graphs that go beyond sort of the typical nonlinear optimization that underlie most of the work that I talked about. So Michael, just say next when you want to advance, and I'll be your slide advancer. And you should unmute.
Thank you. This helps. Thanks. If you think of manipulation, right, then we end up with optimization problems typically that have constraints. And so on the next slide, my PhD student, Paloma Soti, recently figured out how to get hard constraints into the base tree formulation. And so that significantly expands what we can do, what kind of problems we can solve. So for example, we can use contact constraints from manipulation world and use them in the state estimation. That reduces the uncertainty significantly, right? These are equality constraints in the factor graph. But we can also do this in the localization or mapping. So a vehicle cannot drive through the wall, obviously. So that means either the trajectory is wrongly estimated, or if we also do mapping, maybe the wall is in the wrong place. An equality constraint in the factor graph solves this problem. Next slide. And so factor graphs also support modeling of ambiguous situations, but this is where it gets tricky in terms of inference. So in this case, we have a robot that, as usual, has noisy sensors, so it doesn't know exactly how far it moved. And there are two possibilities. Either it sees the same doors that it previously mapped again, or it actually moved a bit further and it only sees the second door and a new door. And so in the factor graph, we can represent this by a multi-mode factor. So that factor would have both options in, and there's a discrete choice, right, as part of the cost function. But this is no longer Gaussian, so it violates the assumptions of our optimization. So how do we solve this? Next slide. One possibility is to do non-Gaussian inference using non-parametric belief propagation on the base tree. This is work by Dehan Fore at MIT. And so he replaced the Gaussian message passing inference on the base tree with passing messages that are approximations of the underlying distributions, and so with kernel density estimates. So they don't have to be Gaussian. So the posterior that comes out of the inference can be non-Gaussian, or it could even be multimodal, as in this case. So if we think of, if the posterior is actually a mixture of Gaussians, next slide, then we can even do something else. So these are Gaussian problems with ambiguity, and here multi-hypothesis tracking can be used. So this simply runs multiple instances of a given inference algorithm. So in our case, this would mean we would run one base tree per hypothesis. The problem with this is exponential growth. The factor graph here has a few colored factors, each one, 6 of them, each one adds an ambiguity. So in total, we have 2 to the 6 or 64 different hypotheses. So this quickly becomes untrackable, right? So we have to prune some of these hypotheses. But ideally, we don't want to prune them too early because it might include the wrong, the actually correct hypothesis. Next slide. So my PhD student who recently defended Ming Xiao figured out a way to use a single base tree to represent all of the hypotheses. And the key insight here is that a lot of these cliques have only a single hypothesis or a small number. That means there is actually redundant computation between the different hypotheses. And here we have to calculate these only once. So we save computation, we can postpone pruning decisions to later, and therefore are more likely to succeed. Next slide. We can in fact use this for mapping. So here's a RGPD mapping using multiple hypotheses, and we can avoid wrong decisions and even get multiple plausible solutions at the end. So on the right, you see single hypothesis. In this case, ISM2, for example, was used, and locally we fail because we choose the most likely option, but that's the wrong one, and we cannot recover. In the multi-hypothesis case, we can recover. And as the top map shows, there are actually 3 hypotheses overlaid here. At the end, we might still not have enough information to determine which is the correct solution. So the question now becomes, how do we figure out how the robot can disambiguate? Next slide. And for this, we can use the knowledge about ambiguity to do planning. If we just look at exploration, then we would do active SLAM. But instead of now just trying to reduce the continuous uncertainty of the state space, so not have the robot's state become too uncertain, we now look at the discrete ambiguity also and take that into account. The goal is to keep the number of hypotheses low, so we ideally never have to do pruning and we won't fail. Next slide. So is loopy belief propagation on factor graphs a better match to the hardware of the future? So Andy Davison recently introduced, implemented factor graphs on a graph processor. So right, we now have a lot of hardware available, GPUs. We have special processors for deep learning now, and even graph processors specifically to do inference. So in this case, loopy belief propagation is very easy to parallelize, and they've shown amazing results with over 30 times speed up for structure for motion. So I think this will heavily influence the kind of algorithms that we go into in the future. And next slide. Now Frank will end the talk with an outlook into the future. Yeah,
so I guess I'm setting up for a debate after the talk at this time. So 15 years ago, we really didn't have a crystal ball, but we certainly imagined more robots than that there are now in our lives, right? So I'll talk about this and maybe speculate a little bit about, with my limited knowledge about what this might be, and I'm looking forward to a debate about this. And I'll go about this in 3 different environments. So first, airborne autonomy. I think the outlook there is relatively positive, and that's maybe colored because of my engagement with Skydio. Skydio definitely has shown convincingly that we can put drones into consumers' hands, that they are safe. There is an occasional crash, and sometimes a small twig is not seen, but the drone is fairly lightweight. Accidents are not expected to be involving injuries or lethal accidents, right? This might be a little bit different if we get thousands of drones like the Google Wing drones or the Amazon Prime Air drones delivering packages to our homes or to distribution points. And we will have to work on assuring safe airspaces. And both NASA and DARPA have been funding initiatives. Skydio actually got a $4 million grant just now from DARPA to make sure that their autonomy stack is really certified. I myself am involved in a joint project with Stanford, where NASA it's led by Stanford, and NASA is basically sponsoring us to think about safe airspaces. And again, crashes of lightweight drones are probably non-lethal. Different is self-driving cars, right? And I think we all imagined the timeline for self-driving cars to be very different. And as smarter people than myself, with more experience in this space, for example, this is a slide from Andrej Karpathy at Tesla. He talks about the long tail, he and other people, in fact, which is the long tail of perception, meaning there are so many situations that are very rare that you really can't train a deep network for all these different situations, right? So the notion that we are going to train ourselves out of the perception problem is probably broken. And Andre and Tesla have a particular answer for that. And I think every self-driving company must have an answer to this problem, right? Be it driving millions of miles or some way to harvest these rare events. And the other is bugs, all right? So I do get on airplanes knowing that airplanes are now driven by software, but once in a while, a software bug has lethal consequences, and this is even in cars without autonomy. So, well, you know, I have worked with companies. I know that some companies use GTSAM and factor graphs, and so I insist on making GTSAM unit tested and safe, but I do know there are still bugs there. This is a movie from Holomatic, which is Kaess company in Beijing, and factor graphs and GTSAM are used successfully there to form the basis of a navigation stack. But to advance certifiable factor graphs for embedded applications, Kai and I recently started a nonprofit initiative called OpenSAM. And the idea is that while GTSAM is great for back office and research, so you know, if you want to calibrate your sensors, by all means, GTSAM is one of the best frameworks there to use. But if you want to make factor graphs work in an embedded context, you need a different type of code. You need certifiable code that doesn't allocate memory. It's really sort of its own little industry on how to code for embedded processors. And we are looking for industry memberships and collaboration. So if you're interested in this problem, do reach out to me or Kai, and we're very interested in talking to you. The most difficult environment, though, to deploy robots in is, I believe, the home, right? And this is because of three very large difficulties. One is perception. I've been involved in perception in indoor situations in many different settings, and the clutter, the occlusion, the variety of different environments, it is just a very challenging problem. If you think that perception in autonomous driving context is hard, it is 10 times harder in a home context. Manipulation in those environments is not yet solved either, right? So I want to highlight this. This actually came out today. This is the new robot by Hello Robot, which is Aaron and Charlie's company. They just came out of stealth today. And they have a very interesting manipulator. So they have a particular vision, which is linear, not rotational, which is quite interesting. But you know, many of the movies that they show even are remote controlled. So autonomous manipulation, very difficult problem, yet unsolved. And as I show, I think factor graphs have a role to play in motion planning and thinking about grasping, manipulation planning, etc. And then finally, there is an HRI aspect, right? So many people are working in this very important field of HRI because the expectations of people and what a robot can do are often very mismatched. We see this not only with robots, but we see this with the virtual assistants like Siri or Google Home or the Amazon Echo, who miscomprehend us all the time. And this doubly goes when there is a robot involved, because now we're going to assume that this robot can clean our floors, can get in all the little nooks and crannies, and it simply isn't true. There is a new effort that I would like to end on that I have started in my lab in a collaboration with Google, which is called Swift Fusion. Because I think the answer here is to combine both deep learning and inference in more traditional graphical models like factor graphs and combine them in a single framework. And Swift Fusion is our attempt to do that. So Swift for TensorFlow is an initiative that was started at Google to provide a new language to interact with deep learning, where differentiability is built right into the language. And this is an amazing match with factor graphs, because every factor is really, in a continuous setting, a differentiable function. And so Swift and Swift Fusion will allow us to talk about factor graphs and dense tensor processing, which you need for deep learning, in a single framework. And that, I think, will enable to combine this probabilistic estimation and optimal control, right, with data-driven factors, like much more in the trend that Jan showed at Imperial and others have been going into as well. We're looking actively for collaborators here. So if you want to collaborate on this, then please direct message me on Twitter, and we can start to talk. I want to end. Michael and me are, and myself are very grateful to all the amazing collaborations that we had over the years, both in academia, on the open source repo, on GitHub, and our industry collaborations, and especially Skydio. So there are probably faces that we forgot. We don't have photos of our GitHub collaborators, so we couldn't put these in, but none of this was possible without the hard work of all these people. So thank you very much for your hard work and your support and co-advising. It's much appreciated. I'd also like to sort of express my thanks to all the people that have contributed images and movies. And so I added all the references to the talk, and we'll make the slides available after the talk as a PDF. So with that, I guess we can open it for questions and the debate.
Thanks, Frank, and thanks, Michael. Super interesting talk, impressive. We are a bit over time already, but we have some interesting questions actually, and I'm wondering whether we could bring also Fabio, for instance, up if he wants to. So Fabio, I kind of allowed you to unmute. And
hi, can you hear me?
Yes, hi Fabio.
Hi Marc, hi. Hi everyone. Frank, that was great. Great vision for the future. I'm a big fan of this work. My question is really related to the structure of the problem, and it seems like in many of these problems, this structure is given or somehow abstracted naturally from the problem. And one question I would have is whether we can embed the learning or estimation of the structure into the problem in further, let's say, iterations of this. Thank you. Great to see your talk.
Yeah, so I'll answer, and then also let Michael answer about, because I think he has an opinion about correspondence and discrete inference. But my answer would be Swift Fusion that's really sort of set up to do exactly that. If we couple TensorFlow, a language where differentiability is first class, and then factor graph, so we can differentiate through the factor graph and through the optimization process. Then we can basically build the learning right into the framework. So we've done baby steps in that direction, right? And others have too. There's this implicit function theorem, right, that's been used to sort of differentiate over optimizers. We've done a more direct route in image alignment. My students, Zoran LV and with Andreas Geiger and Jim Ray, we have a deep, image alignment problem that goes through the entire optimization. So I think putting these all in the same framework is one way I would go about it. Michael, do you want to say something about?
Sure. Yeah. So I think on there are some other baby steps we took on, especially correspondences, where we have factors that have these discrete decisions embedded that lead to non-Gaussian optimization problems. But we still have to specify at the moment the connectivity, right? The factor might connect to two different landmarks, and there's a decision, do we see that one or the other one? But so I think the big question is how can we really learn that structure from scratch? And I think Frank's recent work there might be a promising direction. where that could be possible, could become possible.
Also want to highlight that back in 2003, 2004, Mike Montemerlo had his PhD work was about FastSlam. And this is not very well known, but FastSlam had discrete variables for the correspondence right into the framework. Now, this was solved using sampling over trajectories. And I think we've all been a little bit afraid of putting discrete variables into the optimization with good reason, okay? Because there is exponential blow up. And so the work that Michael did with the multi-hypothesis base tree and work by other people, I'd love to talk more, Marc, about how we can do discrete inference efficiently for things like correspondence over time. So,
okay, thanks. I think I'd rather cut like the Q&A a bit short because we are already 10 minutes late, and I really want to get on stage also the other panelists now. Danica and Gaurav, if you would just show yourself. For this panel discussion, actually, I invited Danica Kragic, a professor at KTH, who is doing like amazing work on many things, actually on grasping, manipulation, computer vision, and always really bridging between these things that many other roboticists actually keep separate, which I find super impressive. And we also have on stage Gaurav, a professor at University of Southern California, who is actually co-program chair at the RSS, where Frank Dellaert actually published this square root SAM, if you remember that, talking about age and things. So it's great to have you both on stage and to bring the discussion maybe to a bit higher level. So let me maybe start asking Danica, as you're new on the stage. So what do you think, like how did the field of robotics develop? And let me just let the question as general as that in the last 10 years.
I had a comment of 15 years that we basically expected more. And I think that what we really learned is, as Frank said, perception is really hard. I think that what we have as the biggest challenge is that we actually control physical systems, right? So we want them to move and we want them to do things. We want those things to be done safely. So I think that this is something that is not well understood by people outside our community. So taking a bit of a problem or a piece of a problem, understanding a scene just for understanding which objects are there, but not for the purpose of grasping or interacting, is of course much less of a problem. The other thing is that I think we do have challenges when it comes, as Frank said, also in domestic environments where we can't have expectations about things not changing, not only on day-to-day basis, but basically on hourly basis. Everything changes. I mean, having kids at home, anybody would know. And then I think that what we also understood is that not everything in our environments is rigid. It's not that things move around, right? They're also deformable. And when it comes then to physical interaction, that puts additional challenges on really modeling dynamics, understanding the physics. So if you wanted me to kind of like just summarize, I think that the robotics is actually as an area a fantastic tool to understand how complex the world around us is and how many competencies we need, everything from physics, mathematics, statistics, and so on, in order to be actually able and develop them. That can do then safe interaction with a human and with the environment. And I think that we did not understand, you can't understand this complexity if you don't start to build systems, because all of these things come very natural to us humans. We take them for granted. But when you have a physical system that has an environment that you don't understand, yes, you build a robot with 6-7 degrees of freedom. We have dual arm robots. We do have some tactile feedback and force feedback, and we believe that that's enough. But when you need to sit down and actually make a model of that system and then try to think how that system should also perform in real time, you can't understand that until you start to build a system.
Okay,
and I think that this was the reason why we have this conference. We wanted to have systems. We wanted to have more systems kind of research to be done. And I think that, well, the conference stands the test of time too, because I think it's a tremendous opportunity to actually appreciate the systems research.
Cool, thanks. So if I hear you summarize that, all the open questions that you mentioned kind of point that we maybe did not solve so many problems in the last 10 years, but actually discovered more problems in the last 10 years. Let me give the word to Gaurav, actually. How do you see it, the development in the last 10 years?
So first, thanks so much for inviting me on. And I completely agree with what Danica just said. There's a real illumination about how different and difficult robotics is compared to some of the other successes that subfields of AI have had. And I think the three things that she outlined really sort of capture that. I think that understanding has deepened in the last decade. Also, before I sort of add to it, I just wanted to give one more round of congratulations to Frank and Michael for really sort of doing the pioneering work that they did. So I remember the first RSS Program Committee meeting where this paper was discussed. And I'm really happy to see that it has stood the test of time. So it's a testament also to the people who reviewed it then and did all the work behind it. So one thing, I think one thing that has been bothering me for the last few years, and I think has now come to the forefront quite a bit, is physical interaction with the physical world. In order to do it efficiently, is very much modulated, it seems to me, by the semantics of what you want to get out of the interaction. So this is, I think, one big barrier between the way we model interaction and what we actually want to get out of it. So this is an old idea in perception, going back to the early days of affordances. So it's not new by any means. But I think this gap has become sort of more apparent to us. One can get exceedingly good at metric representations of the world, and we are getting better at semantic representations of the world. Frank gave some examples of that today. But I think anything we can do to close that gap is going to make things a lot more doable in some sense. I think efficiency and fast inference are going to come because we're going to learn to reason about semantics, because we are not simply going to treat semantics as a fancy way of squeezing it into our way of metric reasoning about the world, but somehow natively develop techniques to deal with semantics. I think there's more awareness of that in the last decade, or at least I hope there's more awareness of that in the last decade.
Okay, cool, thanks. So let me play this back then to Frank and Michael. So the two, Danica and Gaurav, they highlighted all kinds of open questions, so many open questions on the one hand. Your talk, though, was like super enthusiastic about we solved the problems, we solved all problems, and we have the tool to solve all problems. So how do you see this? Like, do you see like that this is a classic in robotics, maybe, that when people actually found like a formal formulation of a problem, then they make super progress, but actually all the other people then actually discovered like problems that don't really fall into this?
I'll let Michael go first.
Yeah, this is a much more difficult question. So, I mean, obviously we didn't solve all the problems, right? I mean, there's more and more problems now coming up, it seems like, that we identify. I think, so factor graphs have been a nice tool, and I think that can be taken further to address some of these problems. But of course, we don't know if this will apply to everything, or if this will be the answer to the problem. And of course, factor graphs are just the mechanisms to represent. The computational mechanisms on top of that might change dramatically, like deep learning, getting deep learning involved in this, for example. Frank, do you have?
Yeah, so yeah, I hope that the last part of my talk was about things that we didn't solve, right? So I agree with both Danica and Gaurav. I think so. Learning the intricacies of our environments and the semantics, meaning what is what objects really matter, what is the fine-grained actual semantic understanding that we need to execute tasks in an environment that might remove this mismatch between expectations of what we can do and what we can actually do. Computationally, it's hard. So I think mostly about algorithms and computation and speed. And I'm very afraid of semantics because of its discrete nature, okay? Because there are so many different categories. And so which label to choose? It's, so if you have 100 labels and 10 objects, you have 10 to the 100 possibilities. Well, that's a lot. And so if you have to evaluate all of them, then you need to, you can't do it by enumerating all of them, right? But I'm very optimistic, and I'll tell you why I'm optimistic. I'm optimistic because deep learning provides a shortcut, right? So earlier in my career, I was very enthralled by Markov chain Monte Carlo, which is a sampling way of calculating posterior probabilities. That's maybe a little bit technical, but the cool thing about MCMC, which is its abbreviation, is that it takes whatever you give as common sense and corrects your common sense. So you can train a neural network to sort of output hypotheses and possible solutions, and then MCMC will sort of correct bring you back to reality a little bit. So I believe that neural networks are not the answer in that they will always give you the true answer, but coupled with fairly old, I mean, Markov chain Monte Carlo dates from the Manhattan Project in World War II, right? So von Neumann and Nick Metropolis were the people that sort of invented those. I think if you take these older graphical model reasoning techniques and deep learning and put them together, to me, that seems like a winning combo. And so I'm very optimistic. It will still take a while, and it will take a while because people are going to be very risk averse to deploying things in environments where accidents are lethal. So maybe we'll see progress first in the home and in the airspace, and then autonomous driving, contrary to all our expectations, might be the last one to really blossom because of the lethality of getting it wrong. So I'll take it. I'm done.
Right. Gaurav, did you want to reply to
that?
I
wanted to jump in and ask. So we didn't say much so far, explicitly at least, about the role of logic in all of this. And Marc, you should also feel free to contribute here, I think, because I mean, are we not talking really about the intersection of logic and geometry at the two sort of, at the very basic level here?
I was thinking exactly about jumping in. I wasn't sure if it becomes too technical, but yes. So Frank, Michael, both you said something super interesting, that you're very much interested in the computation fundamentally, which is cool. I like that a lot. So, and these factor graphs, they relate very strongly, of course, also to optimization methods, linear algebra methods, right? But they do not relate so super well to local optima or to like really discrete things or global optimization, like where there is inherent categorical structure, let's say, or like discrete structure in the problem, like mixed linear programming or so.
Well, if I can jump in, I'll just tell you one little factoid about GTSAM and factor graphs that not many people know. But you can ask GTSAM to solve a Sudoku, which is an inherently logical constraint satisfaction problem, right? So these factor graphs, you can actually encode all these logic problems, and it's in fact exactly the same algorithms that underlie all these navigation and mapping can solve these logical problems. Only they hit computational barriers, much more significant computational barriers. And that's where I think the deep learning will come in and save the day, so.
Yeah, I mean, I see that they're related to CSPs, right? And there's also constraint propagation in CSPs. And if you relax this, then you get message passing in factor graphs. Of course, I see that. But like computationally, it is fundamental that these problems, they have this structure, right? Of course, they can solve Sudokus or so, right? But really hard logic problems, they just have this structure, and if they're both coupled, like the logic with and even first order logic with maybe continuous optimization, it is just fundamentally hard also computationally. I guess the really hard point, so Gaurav, I agree completely with you, the logic is also there in the semantics. The really hard point is, even if you have these cool ideas about how the computation can be done efficiently, doing the science of understanding like the robotics problem well enough to know how GTSAM or whatever can help you to solve them, right? So this mapping between the real world and GTSAM, to put it like that. Maybe that's also the question that Fabio Ramos actually alluded to.
Well, again, answering for myself, yes, I consider myself more of a tool builder. And then you have to form an alliance with people with a real problem. And so the founders of Skydio, for example, had a real problem. They had to put a drone in the hands of consumers and make a reliable autonomy stack. And so I joined forces, and they were really the people driving the application and saying, you know, they've all contributed equally to the autonomy stack. I'm not saying that I solved the problem for them. This was a true collaboration with many more people than just the founders. But going to consumers forms a hard constraint, right? So there is a constraint satisfaction problem there that you have to solve, which is it has to do what the consumer wants. And so it's great to see people like Charlie and Aaron Etzinger, Charlie Kemp, create these new companies to put, you know, robots in the home, because they will be confronted with the same constraint. Now you have to solve the problem, and that, you know, they will not be interested in academic exercises. They will tell you, this is what we want, and we want it yesterday. And so I think these alliances are really great for our field. So, you know, industry, academia collaborations.
Mm-hmm.
So I think structure was brought up before, and I found that really interesting, because it seems even on the continuous side, right, there's a lot of underlying structure to these estimation problems. For example, recent efforts by Luca Carlo and David Frozen, they looked at mapping some of these problems to convex optimization problems. Right? They're actually not as difficult as they originally appear with nonlinear problem with lots of local minima. And so the question is, can this be generalized? Can we? I don't know if we can automatically ever discover these structures, but that obviously would make a big impact. The factor graph itself provides a bit of a structure there, right? It's a trajectory, so they're not independent poses anymore along a trajectory, but they can't move too far from each other. So you can even do sampling over that. Even so it's a really high dimensional space, sampling can potentially be applied and work to some degree, which it shouldn't, right? So this, I think structure is extremely important.
All right. So maybe going a bit back to the original question, also Danica. Danica, do you remember what you actually worked on 10 years ago, and what 10 years ago you thought was super important?
Yeah, the same things I work on now. No, but really, I think that the things that we are talking about now, I think, and why maybe we are not seeing even more progress, especially when it comes to physical interaction, grasping of objects and so on, is that we don't maybe have a very structured way of formalizing the problems we want to solve. So, you know, when we talk about grasping an object, what does that actually mean? What is the expectation? And now, I mean, we are starting to see more and more benchmarks being introduced in the area of robotics. But in order really to see what I would say the same type of science being done in robotics as in computer vision, we would need to use the same type of physical system, all of us. And that's just not viable. So I think what is extremely important for us, and when I look back, I mean, and you and me, Marc, have discussed this, are we solving the old problems, we new methods, or are we really kind of just introducing the problems that are not realistic in order to be able to sell a certain methodology and so on? I think that we do have lots of that in the community, especially now when people from other communities start to, you know, come into our community without really understanding everything else that we have done during the past 10, 15, 20 years. I think that the example of MCMC, Frank, that you gave, it's fantastic, but it does require to have a, you know, the look back capability to be in a certain area for X amount of year and convey the message, convey the history to your students. And I think that, you know, the more time that passes, the more methods that are available and fast fixes and open source software and so on, it's very stressful for new students and for new academics to really go back far enough and to understand whether there is a method that solves the problem in a better way than something that I need to develop from scratch. And this is what scares me, that we just sometimes as academics don't have enough time to look back or to look broad enough to actually understand which methodology and what to use, and then spend enough time on benchmarking and comparing things. Because when we talk about science, when we talk about publishing, I don't think that we have matured enough as a area, as reviewers, to really appreciate good, you know, evaluation, deep evaluations that and require them also. So yes, I do remember what I did 10 years ago, and the reason is that I'm still kind of like working on very similar problems, but I'm trying to understand both the new and the new methods and the old methods better. And that's not necessarily always, you know, resulting in being able to publish about things.
Great. Great. Gaurav, do you have something to add to that?
Yeah, I mean, sure. I mean, I think for me, 15 years ago, one of the big changes in my research life was I used to work with multi-robot systems before that. And I had a sort of very similar thought that Frank said a few minutes ago, which is, if you want hard constraints, you probably don't want to invent them yourself. You want to talk to somebody who lives and breathes those constraints. They force you to think about problems outside your comfort zone. Because, you know, when you're doing your own work, sometimes if something seems so hard, it's relatively easy to say, let's put that aside and let's focus on the piece we know how to solve, right? So about 15 years ago, my group formed a collaboration with colleagues who work extensively in oceanography and marine biology. And it really changed. It gave us a decade sort of work on launching robots into the ocean to do lots of interesting work, particularly in the area of sampling, physical sampling. And underlying it, the sort of problems you need to solve for both estimation and planning for vehicles like this. So it was a real sort of joy to do that. And so that's what I was doing 15 years ago. We still continue that work to some extent. But then about 5 years ago, I became interested in the kinds of problems that Danica and others work on. And we started to teach ourselves a little bit about grasping and manipulation. So we are sort of beginners in that area now, trying to understand where some of the things we know about this entirely different domain can be brought to bear into this for us new area. So I think for me, two things come out of it. One is it's probably may not be a bad idea to sort of switch every few years, every decade or 15 years. And the other is this sort of external constraints. They really act as wake-up calls when somebody says this is a hard constraint, you need to work with me on this. So yeah,
I'd actually like to call out Sid Srinivasa gave a talk in one of the workshops about what problem to choose, and he had a great answer to that. He said, look, there is the things that you know how to do, the skills that you have, and there is the things that people value. And you want to work on the things that are in the intersection of that. And I think what Danica's comment was that there's maybe people that work only in the skills domain and sort of work on unrealistic problems that nobody really cares about, right? And I think Sid called those zombies. So, and we're in a field where progress is incredibly fast at the moment, and literally thousands of arrows are being shot at the same time and you can see sort of what sticks and what doesn't stick. And a lot sticks now, actually. There's a lot that we learn from shooting thousands of arrows and see what sticks. And that's in deep learning. Oh, that works, and that works, and that works, and that works. It's amazing. It's really exhilarating to be in research at this moment to see that. But it's true that it sets up sort of a dangerous mindset on behalf of the students, that they think that this will carry them forward forever, and it won't. Okay. And this is why the combination of these good old, I don't want to say good old-fashioned AI, but good old-fashioned graphical models and inference, it will have to be combined, and it will have to be reinvented. And in fact, many people will create papers and new ideas by going back in time and going back and further in time, as the low-hanging fruit is no longer there. And we've seen that over and over in different fields as well. So I'm optimistic. Yes, it's a little bit scary, and it's definitely scary for new students to enter the field, because you can get scooped by one of these arrows that was pointed in the same direction, and you didn't know about it, and it's on archive, and voila, you have to start over. But I think this will run its course, and then we'll have to go back to deeper thinking. So I'm optimistic there as well. So young students keep shooting those arrows and think about what will stick, and then follow through and go deep. And that's what it is to do a PhD thesis, right? Or go work at a startup and solve a real problem. And that's sort of other type of PhD thesis in a way, right?
Okay, cool. I think in about 8 minutes or so, we actually have the next talk by Luca Calona. Sorry, by Byron Boots. Not that I mixed something up. Byron Boots, sorry. The early career talk. So maybe we cut this short here. I want to thank the panelists here. I think this was really great, really good comments. I liked it a lot. And I liked it a lot that you know, also what Danica actually said last, I like that actually a lot, that it's really important to keep an overview of what has been done in the past, and to try at least to see the relations between new things and old things, and also maybe transmit it to the students and so. And yeah, this whole panel and this whole topic of test of time award is also dedicated to try to not forget about what has been done in the past and what the impact is.
That's right.
And again, congratulations to Frank and Michael to the award, and great work. Thanks.
All right.
Thank you.
Thank you so much for organizing, and thanks.
Bye-bye.
Yeah.
Bye-bye.
Thanks, Marc.
Bye.
Bye.